Hello and welcome. Today we are going to talk about orthogonality of eigenvectors of symmetric matrices. Consider a real symmetric matrix named matrix A. Suppose matrix A has two eigenvectors, named vector v1 and vector v2, corresponding to eigenvalues λ1 and λ2. This means matrix A multiplied by vector v1 is equal to λ1 multiplied by vector v1. And matrix A multiplied by vector v2 is equal to λ2 multiplied by vector v2. To establish orthogonality, take the inner product of vector v2 with matrix A multiplied by vector v1. This can be written as vector v2 transpose multiplied by matrix A multiplied by vector v1. Using the eigenvector equation for vector v1, substitute matrix A multiplied by vector v1 with λ1 multiplied by vector v1. The expression becomes vector v2 transpose multiplied by λ1 multiplied by vector v1. Since λ1 is a scalar, it can be factored out. This simplifies the expression to λ1 multiplied by the inner product of vector v2 transpose and vector v1. Using the symmetry of matrix A, it follows that vector v2 transpose multiplied by matrix A is equal to the transpose of matrix A multiplied by vector v2. Matrix A multiplied by vector v2 is equal to λ2 multiplied by vector v2. Factoring out the scalar λ2, the expression simplifies to λ2 multiplied by the inner product of vector v2 transpose and vector v1. Since λ1 and λ2 are distinct eigenvalues, the inner product of vector v2 transpose and vector v1 must be equal to 0 for this equation to be true. This shows that vector v1 and vector v2 are orthogonal. This proves that for any real symmetric matrix, eigenvectors corresponding to distinct eigenvalues are orthogonal. This property is a fundamental result in linear algebra, ensuring that real symmetric matrices have orthogonal eigenvectors. If you found this video helpful, please like, share, and subscribe for more content on mathematics and data science. Thank you for watching.